Dr. Vijay Lakshmi is working as a professor in the Department of ECE, Anna University, Chennai. She has more than 17 years of experience in teaching. She has published more than 90 papers in international and national journals and conferences. She has organized more than 10 workshops and has attended more than 40 workshops and seminars. She has guided more than 100 projects in both UG and PG level. She is supervising 14 research scholars. She has established an AICTE-sponsored MODROB project for VLSI Lab. She has an endowment award for the top rank holder in PG degree and has 4 cash awards for producing cent percentage of result in Anna University curriculum. She is a life member in various professional bodies like ISTE and IETE. She has specialized in mobile communication, microprocessor and microcontroller, digital system, computer networking, and neural networks.
Welcome to UGC lecture series MATLAB programming. In today's episode, we will discuss about how to generate the MATLAB programming for discrete time Fourier transform. So before developing the coding, first we have to know what is Fourier transform. That is, the Fourier transform may be represented with the continuous signals or discrete time signals. So in today we will discuss about discrete time Fourier transform, its basic definition along with the formula and some examples we will discuss on today's episode. So the first, discrete time Fourier transform. It is one of Fourier transform family. It operates on aperiodic discrete signals. It is used to find frequency domain. Normally the Fourier transform is used for periodic signals. The discrete time Fourier transform is used for the aperiodic signals. So both Fourier transforms are used to obtain the frequency spectrum, which is the magnitude response and phase response. The discrete time Fourier transform formula. So how to obtain the Fourier transform for the given discrete signals? The discrete time Fourier transform is a transformation that maps the discrete time signal x of t, which is represented as x of square bracket n, into a complex valued function of the real value w or omega, which namely it as x of omega equal to summation of n equal to minus infinite to infinite x of n e power minus j omega n, where omega is a real number. Okay, so mostly we are taking the omega value from minus pi to plus pi, which is sufficient to describe all the values. So this is a formula for finding the discrete Fourier transform. Here the n is the discrete time instant, but omega represents the continuous real valued frequency as in the continuous Fourier transform. So this is known as analysis equation. So from the discrete time we are obtaining the frequency, or from time domain to frequency domain. This equation is called as analysis equation. Suppose if you want to find the discrete signal from the frequency domain, or if you want to convert the frequency domain signal into time domain signal, that is called as inverse discrete time Fourier transform. Let x of omega be the discrete time Fourier transform of x of n. Then its inverse is inverse Fourier integral of x of omega in the interval of minus pi to plus pi. That is, we are finding the discrete time signal x of n, which is equal to 1 by 2 pi integral over minus pi to pi x of omega e power plus j omega n into d omega. So this is a formula which is used to calculate the inverse discrete Fourier transform. So now we are calculating from frequency domain, or simply we are converting frequency domain into time domain. So this kind of action is called as a synthesis, or we are obtaining the frequency spectrum to time spectrum, which is a discrete time signal, which is synthesis equation. This equation is called as synthesis equation. So usually these two is called as discrete time Fourier transform pair. This is from the frequency domain to time domain conversion, which is the inverse of Fourier transform. From the time domain signal to frequency domain, this is called as a Fourier transform, right. So usually we are represented this as the discrete pair, which is a bidirectional arrow, x of n into x of omega, or you can call it with e power j omega. So after obtaining the x of omega, right, from the time domain, now we get it the some frequency domain. From that we are obtaining the magnitude spectrum and space spectrum, or it can call it with the frequency spectrum. So in the frequency spectrum, how we are obtaining the x of omega after calculating with the help of that formula, DTFT formula, we are taking modulus of that value and exponential of angle of that value, right. So the modulus value is called as a magnitude spectrum, angle of x of omega is called with the phase spectrum. The absolute values how we are calculating is square of the real and imaginary values. The phase spectrum, which is the angle of x of omega, which is calculated with respect to minus tan inverse of imaginary part divided by real part. Okay. So the magnitude is always represented in the decibels. So before starting the discrete time Fourier transform, we have to use some convergence. It should satisfy this, that is, in order to discrete time Fourier transform to exist, the series summation of integral n equal to minus infinite to plus infinite x of n e power minus j omega n must converge. That is, in other words, it should be limited within less than infinite. The convergence of xm of omega for three different types of signals to be studied are satisfied. The first one we are expecting, it should be absolutely summable signals. X of n is absolutely summable if and only if the summation of n equal to minus infinite to plus infinite, x of n less than infinity. In this case, x of omega is always exist because of this condition, which is a bounded condition. Second one is energy signal. Here the x of n is an energy signal if and only if E of x equal to summation of n equal to minus infinite to plus infinite x n of square, which is less than infinite. Then we can show that xm of omega converges in the mean square sense to x of omega. With this integral, we are satisfying the energy signal also less than infinite. Suppose the mean square sense convergence is weaker than the uniform, then the signal is always convergence. The power signal, third signal, which is the x of n, is considered as power signal if and only if the power signal Px equal to limit we are applying n tends to infinite 1 by 2n plus 1, the summation over minus n to plus n xn of square, that value should be less than infinite. That is, the value should be absolutely summable, then energy signal and power signal should be less than infinite. That is the convergence of discrete time Fourier transform. Now we will solve some example. So first we are taking this example, find the DTFT of the unit sample signal. So unit sample signal is, we are take it as x of n, right? The input signal is given as del of n. This is a representation of sample signal, right? The value represents unit sample, so automatically that value become 1. So before calculating that, first I have to write the formula. So this is a formula, x of omega, DTFT formula. X of omega is equal to n equal to minus infinite to plus infinite x of n e power minus j omega n, right. So now what is the x of n value? X of n value is del of n, simply substituted. Now what is the n value? N value is occur only for the 0, right. So no need of the summation, this value is 1 into e power minus j omega into 0. So automatically this becomes 0, so e power 0 value was 1, right. Suppose if you want to take it with a delayed response, which is n minus n naught, then simply substitute it, then you get instead of n you will put the value as n naught. Here the n equal to 0, this is the delayed value, right. So, n equal to 0 you get it like this. Suppose n equal to n naught means instead of that 0 you are writing it as a n naught. Another example I have taken as x of n equal to a power n u of n. So, which the modulus value which is less than 1. So, first we have to write the formula x of omega is equal to summation of n equal to minus infinite to plus infinite x of n e power minus j omega n, right. So, instead of x of n now I have to write it as a power n u of n e power minus j omega n. So, what is the meaning of u of n, which is a unit step signal, right. So, which always obtained from 0 to, this is a discrete signal. So, you may write it 0 to plus infinite, the value is 1, from 0 to minus infinite the value is 0. So, this summation may be divided as n equal to minus infinity to 0 plus summation n equal to 0 to infinite. So, from minus infinity to 0 this value is 0. So, remove it, you consider only n equal to 0 to infinite. So, 0 to infinite, with that what is the value, magnitude value, the u of n value is 1 into a power n e power minus j omega n. So, now I taken the n as common, a into e power minus j omega into n. So, summation of n equal to 0 to infinite x power n is represented as 1 by 1 minus x, right. Or so, based on that now I replaced with 1 by 1 minus, instead of x what I have, a into e power minus j omega. Suppose for that if you are taking modulus x of omega, then you get the magnitude spectrum, then angle of x of omega if you are getting, then you can get the frequency spectrum. This is a complex number, right. So, from that you can get the magnitude spectrum and frequency spectrum. Suppose if I have taken the another example x of n equal to cos omega naught n. So, how I have to write it, the formula x of omega is equal to summation of n equal to minus infinity to plus infinite, okay, x of n e power minus j omega n. If I take it with n is greater than 0, then I can change the limit n equal to 0 to infinite, x of n value is taken as cos omega naught n into e power minus j omega n. So, in that case I couldn't continue this process. So, I have to use the trigonometric form for cos omega naught n. The cos omega naught n can be written as half, that is like how we are writing the cos theta value, cos theta equal to e power I theta plus e power minus I theta divided by 2, right. So, instead of theta what I have, omega naught n. So, simply replace it, e power j or I omega naught n plus e power minus j omega naught n divided by 2. I split it as 2 terms, right. Now, this term is multiplied with e power minus j omega n, this term also multiplied with e power minus j omega n. So, after that what you have to do, you take the common terms. So, finally, you get the answer as, because after simplifying you get the 1 plus cos of twice of that value. So, finally, you get x of omega equal to summation of k equal to minus infinity to plus infinite pi of del of omega minus omega naught plus 2 pi k plus del of omega plus omega naught plus 2 pi k. So, in the discrete time Fourier transform, after obtaining its magnitude response, it shows like this. So, by varying the constant value m equal to 6. So, it will shows the 6 peak values, right, the sine wave modulations. This is a magnitude response for the rectangular window. So, by varying the m value as 9, you can find the ripples. So, m equal to 15, the number of ripples are increased, this is a 35. So, more numbers. If you are giving n equal to 100 or 1000, it comes like a straight line. So, after executing the program, by varying this m value, we can check its magnitude response. This is a simple response which m equal to 6, right. So, where we are expecting the 6 peaks 1, 2, 3, 4, 5 and 6 peaks values. This is the magnitude response. In case of phase response also, you can identify that the 6 values, right. So, this way after executing we have to verify our output. So, now I will take one example, x of n equal to e power minus 2n, okay, where n is greater than 0. So, now we have to write the formula x of omega is equal to summation of n equal to minus infinite to plus infinite x of n into e power minus j omega n. Now, I will substitute the value summation of n equal to 0 to infinite, which represents greater than 0. For x of n, I will take it as e power minus 2n into e power minus j omega n. So, after substituting, now we have to simplify n equal to 0 to infinite e power minus 2 minus j omega into n, right. So, according to the formula, it can be simplified it as 1 by 1 minus e power minus 2 minus j omega, or it can be written as 1 by 1 minus e power minus of 2 plus j omega. So, this is the value of x of omega. So, this is the way we are finding the discrete time Fourier transform. Now, we have to develop the MATLAB coding for this example. So, I have given the MATLAB coding. So, after executing this exponential example, so this is a magnitude response, right, with absolute value of x as a magnitude and frequency in the y direction. The phase response, the angle of x value with the frequency I have taken. Suppose I have given the n value was minus 1, then the response is varying, especially the phase response is completely differ compared with the previous case. This is a Fourier transform program for continuous time signal. So, first we assign the frequency value, that is W value, which is taken from minus 10 to 10 with a period of 0.02. Okay, if I have a constant, then I will write it as the equation x equal to 1.0 divided by 2 minus j omega. Now, I want to plot its response. You can directly plot W comma absolute value of the answer comma W comma angle of your answer capital X. Okay. So, now save your program, FT for continuous time. Now execute it. Capital X, angle value of capital X. Is a case sensitive, so we have to give it properly. So, now you get the signal, right. This blue color line is a magnitude response, the green color is a phase response. Another example is we have discussed about how to develop the MATLAB coding for the rectangular signal. So, the rectangular signal is like this, right. So, for this rectangular, how to develop the MATLAB and how to obtain its magnitude and frequency response. So, this is a magnitude response for the rectangular pulse, this is a frequency response when I have considered the A value was 2. By varying the A value, you can get the different magnitude and the frequency response. You can view the changes. Another problem, just I am replacing the x value sine function, that is 2 into sine of A multiplied with omega divided by omega. Okay. So now plot frequency with respect to magnitude and frequency with respect to angle. So save the program and execute it. So this is a magnitude response blue color line, the green color represents the phase response of the sine function, or it also sinc function, right. This is a response of continuous time rectangular window signal. The another example, which is x of n is equal to 0.9 power n. Okay. So this example has solved and developed the MATLAB coding. Its response is like this, right. This is a magnitude response for 0.9 power n. It is obtained with absolute value with the frequency. The phase response is angle of that x value and the frequency value. So now we will execute this in MATLAB coding. So clear all, assign the n value from -5 to +5, then k value is varied from -200 to 200. Now take the w omega value, omega equal to pi by 100, that is pi k by n. Then x, this is actual expression, x equal to 0.9 power n. Is element wise we need a power, so dot power n. Now obtain the expression x, capital X equal to x multiplied with exponential of minus j into pi by 100 power of n transpose star k. So now we have to get the absolute value and angle value. So I assign some variable. So magnitude of x equal to the absolute value of answer capital X. Okay. Then the angle value of capital X is assigned with an x. Okay. So now we have to subplot, that is 2 column with the first one. So now plot w by pi comma magnitude of x. If you wish, you give the grid value, then assign the labels. So before assigning the label, you give the axis. It varied from -2 to 2, then -1 to 1. So now give the labels, x label as frequency, y label as absolute of x, and title as magnitude response. Okay. So now plot the phase response, plot 2 comma 1 comma 2, plot w by pi comma angle x. So this is a case sensitive, we have to give the titles very properly. So, grid, then give the labels. Axis is -2 to 2, then y axis also -2 to 2, then x label as a frequency, y label as a angle, then phase response. Now save the program as FT. So, after saving the program, now execute. So, now you get, this is a magnitude response, this is a frequency response, that is phase response of your program. Summary, in today's session we have discussed about what is discrete time Fourier transform and how to obtain the Fourier transform for the discrete signals and what are the formulas we are using and what are the convergence of discrete time Fourier transform, and we have solved some examples and developed the corresponding MATLAB coding. Questions. Write the formula of inverse discrete time Fourier transform. List the convergence of discrete time Fourier transform. Find the discrete time Fourier transform for unit step sequence and write the MATLAB code. Find the discrete time Fourier transform of the rectangular pulse sequence x of n equal to u of n minus u of n minus capital N and obtain its spectrum response using MATLAB coding. With this, I will wind this session. Thank you.